This lecture is on the t-test for independent means. This is going to be a follow-up to the first lecture on t-test for independent means. So this is part 2. So again, just to review, we've done 3 different types of t-tests. And I like to think of these t-tests as different tools that I have in my toolbox when I'm doing different research projects that require different statistical analyses. So occasionally, we'll need to compare a sample mean and determine whether it is significantly different than a known population mean or some logical comparison value, but we don't know what the population variance is. And so in this case, we're going to do a single sample t-test. There'll be other research situations or designs where we've got a repeated measures design. We get 2 scores from each person, and we want to calculate whether there's a change from, say, time 1 to time 2, or from a pre-test to a post-test, or before and after an intervention, whether that change is significantly different than 0. In that case, we'll use a t-test for dependent means. And then there's other research situations where there's 2 groups that we want to compare. And so that might be existing groups like men versus women. It might be people that have a college degree versus people that don't have a college degree. Or it might be groups from some sort of a research study or an experiment. So maybe one group that received a treatment and one group that didn't. One group that received an experimental manipulation and one that was in a control condition. So when we're comparing 2 means from 2 separate groups, each person in the group only has 1 measurement. We're going to use that independent means t-test. And in all 3 of these hypothesis testing situations, we don't know what the population variance is. Okay, so with our t-test for independent means, we're going to use our sample data, all kinds of stuff here. We're going to use our sample data, and we're going to come up with an estimate of population variance for both of our populations. We're going to use that estimate of population variance from both populations. We're ultimately going to pool that together. We're going to come up with a single estimate for population variance. And I'll review the reason why we do that in just a little bit. But from that pooled estimate of variance, we'll use that to calculate the variance of the distribution of means that comes from each population. So again, you can think of each distribution of means as the result of a random sampling process. This distribution of means conceptually answers the question, what happens if I take a repeated number of samples of a particular size from this population and calculate the mean? What we get is a distribution of means. So we can determine what the variance of that distribution of means is for our first distribution and our second distribution. And then once we know both of those variance estimates, we're going to add those together and get the variance of the distribution of mean differences. So this conceptual entity we learned about last time, this is a distribution of mean differences. A distribution of mean differences is formed by randomly sampling 1 mean from this distribution of means, randomly sampling a mean from the second distribution of means, calculating the difference between the 2, and then placing that difference in this distribution. You can think of this as a pile of differences. You'll notice that most of the differences in this distribution of mean differences are centered around the value of 0. That's because under the null hypothesis, we expect that if all the means in this pile and all the means in this pile are ultimately sampled from 2 populations that have identical means, that over the long run, if I randomly sample a mean from this pile and I randomly sample a mean from this pile, most of the time we should get means that are the same, that on average they're equal, okay? Because that's the most frequent value. And so when we do that, we get a mean that is equal to this mean, and we calculate the difference on average over the long run, we're going to get a difference that is 0. Sometimes we get a mean difference, or a difference between those 2 means, that is greater than 0. That could happen by sampling a mean from this distribution that's larger than a mean from this distribution. So we get a positive difference. Sometimes we get a negative difference. How would that happen? We get a mean from this distribution that is smaller than a mean from this distribution. So when we subtract the two, we get a negative difference. Okay. So, but in this distribution, most of those differences should be zero. Some will be positive, some will be negative, but there should be very few large differences and very small, and also very few large differences that are negative. So very few large positive differences, very few large negative differences. And then our t is calculated as the difference between our two means evaluated over the standard error of the difference. So ultimately, we're trying to figure out from our estimate of population variance, from our variance of the distribution of means, from our variance of the distribution of mean differences, and then ultimately the standard deviation, which is the standard error, on average, what would be like a typical difference between those two means based on this random sampling process. And therefore, we can evaluate what is the actual difference that we're observing between our two means. Like if we're actually doing the study and we've got our treatment group and we've got our control group, we know ahead of time what's a difference that wouldn't be unusual. But if we see a large difference between some treated mean and an untreated mean, and it's too large to fall in this distribution, we're going to say to ourselves, okay, well, the null must not be true. I'm going to reject the null hypothesis. And I'm going to instead find support for my alternative hypothesis, whatever that is. All right, so that's just an overview of the logic that I reviewed in the first lecture on our independent means t-test. All right, so a couple assumptions. The first is that our two populations are normally distributed. Otherwise, a t-distribution is not appropriate. Our t-distribution is our comparison distribution for when we calculate our t-statistic. We're going to place that statistic in a t-distribution. So if our two populations are not normally distributed, we can't use a t-distribution. But it turns out that this is really only an issue if both populations are extremely skewed and in the opposite direction. So if for some reason we had reason to believe that population 1 had scores, let's just say that these are scores on some like an examination in a stats class, and we're interested in comparing men and women as just for example, we would have to have very strong reason to believe that men as a group had exam scores that would say be very positively skewed. So like maybe most men don't do very good, and so there's a very strong positive skew. And women would have a population of exam scores that is very negatively skewed. So it's only when they're very strongly skewed in opposite directions that this assumption is violated. So the short of it is, this assumption is hardly ever violated in practice. Okay, so the t-test holds up even when the shape of the populations is fairly far from normal. A second assumption is homogeneity of variance. And this is really the assumption behind why we pool the variance together to get that single pooled estimate of variance. And so to do a t-test, we have to be able to assume that the two populations have the same variance. Without this assumption, it just wouldn't make sense to pool the variance, to pool together those two separate estimates, which we ultimately use to get the pooled estimate of variance, and then ultimately use that to determine the standard error of the difference. However, this is something else that statisticians have determined that the t-test is robust to, and so the t-test can be accurate even when the two variances are estimated to be very different. And it is beyond the scope of this class, but there are ways to mathematically determine whether the population variances are assumed to be equal or not. Beyond the scope of this class, but it's worth knowing that it is an assumption of the t-test that the two populations have equal variances. A third assumption is that observations from people in each group are independent. So what one person does in group A has no bearing on what somebody does in group B. How men score on an exam in stats class has nothing to do with how women score on the stats class. So these groups really must be independent. Their scores have nothing to do with each other. The variance of the t-distribution is calculated by assuming a random sampling process. And so that is a fundamental assumption, is that the observations have to be independent. The reason is because when scores are not independent, they are more similar to one another, and the result is less variability than if the scores are independent. So our estimate of standard error would be lower than it should be if we have scores that from the two different groups that influence each other versus are completely independent. And when we have a lower standard error, we're more likely to get a statistically significant result than we normally would. So, all right. Let's go through another example, which should give you a better sense of how to calculate our t-test. So a study by Brady and Halpern Felsher in 2007 examined the positive consequences that adolescents reported that they experienced due to having sex. And so one of the research questions was, among adolescents who have sex, is there a difference between boys and girls in their perceived popularity? That is, do adolescents think that it's a cool thing to do to have sex, and they think that if that reputation gets out, they will be perceived as more popular by their peers? All right, so here's some numbers. These are based on this study, but I've just made them up for the purposes of this example. Okay, so what we have here are 27 boys, 27 girls, and then what we have here is the average in their perceived popularity. And so higher numbers equal more popular. So what we can see is that on average, boys who have sex perceive that they're more popular than girls who have sex. And then we've got a standard deviation. Now, what's being reported here is the sample statistic, the descriptive statistics standard deviation. So we'll have to do something with that number in order to convert it to an estimate of population variance. But when you read a research article in psychology or in other disciplines that are social behavioral sciences, what you're likely to see in the report is the mean as well as the standard deviation, as in the descriptive statistic, for the two groups in the study. All right, so what we're going to do is we're going to use our 5 steps of hypothesis testing. We're first going to restate the research question as a research hypothesis about populations. And I'm just going to say arbitrarily that boys are population 1 and girls are population 2. You could flip-flop that. It doesn't matter. But when you have a directional hypothesis, it's important to keep track of who's population 1 and who's population 2, so that when we subtract M1 minus M2 in our t-test formula, we'll know what the predicted direction of the result will be. That is, we'll know which side of the distribution to look on. Okay, so for our purposes here, we're just arbitrarily going to call boys population 1 and girls population 2. So our research hypothesis is that boys and girls who have sex differ in their perceptions of their popularity. Notice that that is a non-directional hypothesis. So we're going to predict that mu1 is not equal to mu2. Now we took a look at the data, but you have to imagine that ahead of time, before we did the research study, before we even collected the data, we had this hypothesis, and that's what motivated us to do the study and go out and collect the data. So the idea is before we even have our data, we have the hypothesis. So even though I showed you the numbers on the previous slide, the hypothesis would be generated previous to getting the data. All right, so we're just going to have a non-directional hypothesis here that mu1 is not equal to mu2. And again, just coming back to a point that I've tried to reinforce, hypotheses are always made at the level of populations. We're not making predictions about M1 and M2. We're making predictions about mu1 and mu2. Okay, population averages. The null hypothesis is simply then the opposite, that boys and girls who have had sex do not differ in their perceptions of their popularity. That is, mu1 should equal mu2. Oops. All right, animations are a little off here, but the next thing we need to do is determine the characteristics of the comparison population. We should know now, having heard the conceptual reasons for it, that our comparison distribution is a distribution of mean differences, or a distribution of differences between means. And that distribution will be centered around a mean of 0, because if the null hypothesis is correct, we don't expect there to be any difference between boys and girls in their perceptions of their popularity. And that's at a population level. And so when we randomly sample any two means from each of those populations and calculate the difference, we expect that that difference would be 0. But what about the standard deviation, otherwise known as the standard error? What is the standard or average amount of error we can expect between any two randomly sampled means? So even under the null hypothesis, if it's true that boys and girls do not differ in their perception of popularity, under the null hypothesis, if we randomly sample 27 boys and we randomly sample 27 girls, calculate a mean for boys, calculate a mean for girls, we aren't going to expect that the mean is exactly 0. Like, that's our best guess, but we're willing to say there's bound to be some error, right? There's bound to be some standard error. So we need to figure out the standard deviation of that comparison distribution. We do that by figuring out the estimated population variances, using our raw data, getting sum of squares and dividing that by degrees of freedom. And so what I wanted to illustrate here is that it's possible, given the descriptive statistics, to work backwards. Okay? We'd have to think about how this would be done, but we know that a standard deviation we get by taking the square root of the variance. The variance is sum of squares divided by n. So what we can do is we can figure out the sum of squares if we know what a standard deviation is, and then once we get that sum of squares, we just divide by degrees of freedom, and that will give us an estimate of population variance. Okay? So the short of it is, if you know what standard deviation is as a descriptive statistic, you can work backwards and determine the estimate of population variance. So I've just done that for you, okay? And that's what this point was. Okay, so once we've figured out what our estimate of population variance is from both boys and girls, our estimate of population variance for boys is 72.23, and our estimate of population variance for girls is 42.01. Because of the homogeneity of variance assumption, we're going to pool those estimates together. We do this by taking a weighted average. We're going to weight each estimate of variance by its sample size. Notice here that sample size is equal. And so it's possible to just take the simple average of 72.23 and 42.01 and simply average those together, and that will give us our pooled estimate of variance. But I'm still going to go through you could say, calculating it the kind of the more complicated way of taking the weighted estimate. All right. So degrees of freedom 1 is n minus 1. So n1 is 27. 27 minus 1 is 26. Okay. Because girls have the same sample size, degrees of freedom 2 is also 26. We get total degrees of freedom by adding together degrees of freedom 1 and degrees of freedom 2. So 26 plus 26 is 52. So what you can see is that boys represent 26 over 52, in other words, 50% of the total data, and girls represent 26 over 52 is 50% of the total data. So we're basically saying, let's multiply this by 1/2, and let's multiply this estimate by 1/2, which we'll do, and then we'll add those back together. And that's our pooled estimate of variance. So if this is kind of just to illustrate why that weighting procedure works even when sample size is identical. But if you just add 72.23 plus 42.01 and then divide by 2, you'll get this exact same answer. Okay? So that's our pooled estimate of variance. From our pooled estimate of variance, we're going to get the variance for each of the distribution of means. We do that following Rule 2a, where we're just going to divide that pooled estimate of variance by n. In this case, again, it's a more simplified example than last time. N is the same, so that makes our calculations easy. So we're going to get the variance for the distribution of means for boys is 2.12. The variance of the distribution for girls is also 2.12. Based on the variance sum law, we're going to add those two variances together to get the variance of the distribution of mean differences. Okay, the variance of that distribution of differences between means. And then the last thing that we're going to do is we're going to take the square root of that variance to get the standard deviation, otherwise known as the standard error. And this 2.06 is directly interpretable. What that is telling us is that we can expect any two means that we sample from our population of boys and our population of girls to differ by 2.06 popularity points. That was the metric that we're using. Okay? So it wouldn't be weird or it would not be unusual to take a random sample of 27 boys from a population in a random sample of 27 girls from a population of girls, calculate the mean for boys, calculate the mean for girls, subtract one from the other, and seeing that there was a difference of 2 points, that wouldn't be very unusual at all. That would be like a standard error. That'd be a standard difference. Okay, and so that becomes the denominator of our T formula. All right, so to get a critical value, we need 3 pieces of information. We need degrees of freedom, desired significance level, and then whether we're going to conduct a 1 or 2 tail test. Degrees of freedom we already determined in order to come up with our pooled variance. But again, just to show you, we're just going to take our 2 different degrees of freedom and add that up. So our total degrees of freedom is 52. We're going to do a 2-tail test because we had a non-directional hypothesis. We just predicted that there would be a difference between the means. We didn't say that one would be greater than the other. And then by convention, we're going to use an alpha of 0.05. So we have to just look up the appropriate value in a t-table. That value is plus or minus 2.01. Again, you'll notice that it's plus and minus because of our 2-tail test, our non-directional test. We're going to look on either side of the comparison distribution. Just to show you where that number came from, here's our t-table. Once we start getting degrees of freedom past 30, the table starts jumping in increments of 5. So we landed here at 52, which is between 50 and 55. So what do? We'd have the choice of using 2.009 or 2.004. By default, we're going to go to the higher of those 2 numbers because it's the more difficult critical value to surpass. So when in doubt, you make things more difficult on yourself. Now, in practice, people don't really use lookup tables anymore. We have statistical software that will tell us exact critical values or even exact p-values. Okay, so when this is done in practice, we let a software analyze our data for us. It will spit out a t-statistic for us, and then it will tell us whether that t-statistic is significant or not, and even what the exact probability of getting that t-statistic is. So it's kind of, it's an older practice to use these lookup tables, but this is the way that we teach how to do these statistics in an introductory statistics class before learning the software, so you can kind of get a sense for what the logic is. Because it's really the conceptual logic that's important. That's what we're trying to teach you. All right, so anyway, that's how we get our critical value in this case. All right, so next thing we need to do is figure out our sample score on the comparison distribution. So to figure out that t, we're going to use our t formula for independent means, which is to take the difference between mean 1 and mean 2, and then evaluate that over the standard error of the difference. So mean 1 was associated with population 1, which we had arbitrarily said was boys. Mean 2 associated with population 2, which is girls. So just looking back at the previous lecture slides where I reported the descriptive information, boys had an average perceived popularity of 22.29. Girls had an average perceived popularity of 15.33. We're going to divide that by our standard error of the difference. Our t then becomes 3.38. We're going to decide whether to reject the null hypothesis by evaluating our actual t against our t critical. Because our actual t is more extreme than the critical value, we're going to reject the null hypothesis. What does that mean? Well, a difference between means this large is unlikely to happen by chance if there's really no difference between the two groups. So again, under the null hypothesis, we're predicting that those means are equal, and therefore when we do a random sampling process, we expect that within some amount of error, those means are going to be the same within a certain amount of error. Well, what we're seeing is that difference between those two means is too large to say that it is in kind of within the accepted range of error under the null hypothesis. That t statistic is telling us that the difference between our two means is 3.38 standard errors away from the expected difference of 0 under the null hypothesis. And that's too many. We were willing to live with, under the null hypothesis, 2.01 standard errors above or below the mean. Okay, but we're deviating from that difference of 0 by 3.38 standard errors, and that happens less than 5% of the time if the null hypothesis is true. So because we would get a sample result this large that happens less than 5% of the time if the null is true, we're going to reject the null. We're going to say that's just too unlikely. It's too unlikely for the null to be true. Okay, so therefore, it's more likely that the two populations have different means, and specifically that adolescent boys who have sex perceive that they're more popular than adolescent girls who have sex. Why are we able to make the conclusion that boys perceive that they're more popular? Because their mean was higher. Their mean was 22 point something. Girls had a mean of 15 point something. So we can interpret that mean difference as being indicative of, at a population level, adolescent boys who have sex perceive that they're more popular than adolescent girls that have sex. All right. In addition to statistical significance, it's possible to say something about the size of the effect. So we learned about effect size in previous lectures. But we can calculate effect size for independent means as well, and it's based on a similar formula. So indeed, the basic formula is to take mu1 minus mu2 divided by population standard deviation. We're just going to modify that basic formula using the information that we have. So we're going to substitute mean 1 for mu1 and mean 2 for mu2. And then as our estimate of population standard deviation, we're just going to use the pooled standard deviation, which comes directly from the pooled variance. Okay, so here's our effect size formula for a t-test for independent means. So from this previous example, looking at boys and girls who have sex and their popularity, we had calculated that the pooled estimate of variance was 57.13. So if we take the square root of that pooled estimate of variance, we get 7.56. This becomes our estimate of the standard deviation in the population. And therefore, we can use that as the denominator of our effect size formula. And so we're just going to look at this mean difference and evaluate it over the population standard deviation. That's going to give us a D of 0.92. And the same effect size conventions apply. So D of 0.2 is small, a D of 0.5 is medium, and a D of 0.8 is large. So we've got a large effect here. We can say that there's a large effect. That at the level of populations, we can say that there's not a lot of overlap between boys perceptions of their popularity and girls' perceptions of their popularity. And in fact, on average, there's an average deviation of almost one standard deviation between boys and girls. Okay, now that's not to be confused by a standard error, but among the individual scores, there's on average there's a difference of nearly one standard deviation. So when reading a research report, you might see this. If you read a journal article or the article in which this study was originally published, they'll report the descriptive statistics for boys and girls with a mean popularity rating as well as a standard deviation. And then they'll say, hey, we did a t-test. This was our t. You'll notice that they'll have a little indicator to say that it was statistically significant. And then here's the effect size. You might see in a write-up a statement like this: among adolescents who have sex, boys perceive of themselves as more popular, mean is this, standard deviation this, than girls do, mean. And then here's a t-test. T with 52 degrees of freedom, we calculate a value of 3.38, p less than 0.05, so that's indicating that we have a statistically significant result because the probability of getting these results, if the null is true, is less than 5%. Okay, that's our definition of statistical significance, and then effect size. So when you read research, this is information that you're likely to encounter. And so you've got all the conceptual background for what is going on here and why it makes sense. But as a consumer of research, you could read a statement like this and say, okay, I know they did a t-test for independent means, and I know what they're saying here. They're saying p less than 0.05. They're saying that there is a statistically significant difference between those two means. And I should know that that means that at a level of population, boys perceive themselves as more popular than girls do, okay, when they're both having sex.